All right, class. This video is going to introduce the idea of SIR modeling. SIR modeling is used to model how viruses spread. They're built on the idea of differential equations as a tool to watch how populations can move between different categories. So here's our first example we're going to work on today. The S, I, and R in an SIR model stand for susceptible, infected, and recovered. And what we can do with one of these models is track how their interactions between different groups can cause people to move from one group to the next group. So I'm going to start off with an example of what this looks like on our board over here. So here's what an SIR model can do. SIR stands for susceptible, infected, and recovered. For this model, we're assuming that our population is closed, that all of the people remain in our population, no new people come in. We're also assuming nobody is dying from this particular illness. So we've got an opportunity here for our susceptible people to move to the infected category, and also for the infected people to move over to the recovered category. How do we know how many are moving from one place to another? Well, that's going to depend on some assumptions about what the model looks like, how infectious or contagious our illness is that we're playing around with, and just a number of factors like that. So first, let's talk about how folks are going to move between susceptible and infected. That's probably our most interesting one. Recovered will be a little bit easier to sort out. So, all right. So let's say we have an illness and we have 110 people in a school and 2 of them happen to be infected. How does the illness spread between 2 people to the rest of the 108 people in the room or in the building? So what we can think about is having those 2 people, and each of those 2 infected people could interact with 108 other people, the people who aren't sick yet. And if we multiply together, we're going to find out how many potential interactions there are. And we're going to get that there's 216. Oh, 216. All right. That doesn't seem like too many of them. What if there were more sick people and less healthy people? What if there were just 3 sick people and now there's 107 healthy people left? Now we're looking at a possible of 321 interactions. So just by having one more person get sick, we've got more interactions possible between the sick and the healthy. When the sick people interact with each other, they don't really do anything, and when the healthy people interact, they don't really do anything. It's those cross interactions we're worried about. So if we've got 10 people who are sick interacting with 100 people who are well, now we're up to 1,000 possible interactions where an illness can get transferred from one person to another. Worst case, we could get half the people sick. Maybe we'll do 50 sick and 60 healthy. Now we're looking at 3,000 possible interactions. Now, each interaction doesn't guarantee that somebody's going to get sick. It's got a probability associated with it. So what we're going to do is take our interactions and multiply them together. So we know we've got infected people times sick people. And then we're going to include a coefficient on there that's going to help us know about what the probability is that somebody's going to get sick. We're going to assume K is actually really, really low, but with a lot of interactions, even a really low K value will get more people sick. Here we go. For our particular problem that we're going to play around with today, we're going to make K be 0.006. That's kind of the ballpark of numbers we're going to be expecting for those probabilities. When 2 people interact, it's not a guarantee that someone gets sick. In fact, it's less than 1% for this particular model. But as we saw, there might be 3,000 interactions, so less than 1% still does build a lot more people getting sick according to this particular model. So if you want to think about what K means, since it's a probability, one thing that you're hearing a lot about in the news right now is how to lower the spread of the virus that's in the headlines. To lower coronavirus, one thing that they're encouraging us to do is maintain social distancing and to quarantine. These are attempts to lower that K value as much as possible. If we can cut it in half, we're going to see how big of an impact that would have on our model in just a few slides. So in addition to figuring out how people are going to move from susceptible to infected, which we should have kind of right over here, that's our K times I times S, we also have people moving from infected over to recovered, and that's going to be a little bit simpler of a calculation. The only way to move from infected to recovered is with a probability. For now, that's going to be our limitation. So I'm going to call that probability, I'm just going to call it an R times the number of people in the infected group, and that way we can see people moving from one group over to the other group and watch how they're interacting with each other. We're going to use an R value of 12% for this one. The rate at which people recover, of course, depends on the illness. There's a number of other factors we could put in, splitting people in different age groups and looking how different ages recover. That would be a more complicated model than what we want to start with for our first problem. All right, so we're going to model this now in Excel. What we're going to do is build an Excel chart that's got 5 different columns in it. I'd like you to build along with me, so if you need to pause the video to build your chart, go ahead and do that. You've got that option. We're going to have a time category. I'm going to start my time at 0 and then move up from there by 1 day at a time. We're going to have susceptible, infected, and recovered, and then total. Total isn't really necessary for our model, but it helps to make sure we haven't lost anybody, because sometimes you'll find that you're building your model and you've moved someone from infected to recovered, but then they didn't actually get to recovered in your model, so you would lose track of people. So I'm gonna keep them in there just to help me out. I'm starting off with a case where I have 108 susceptible people and 2 infected in my population of 110. And depending on how many I started with infected, it would change how the model behaves, but that's a good starting point. So for this part, I'm going to jump over to Excel and model it over there. So I better erase my variables up here. And we're going to see how those variables can come into play inside of our Excel sheet as well. So let's go up here. Our susceptible group. So the susceptible group starts at 108, and from there we'll only go downward. That's because once people are susceptible, they move to illness, and then they don't get sick again. So they're just going to decrease until there's nobody left in that category, or until the disease kind of finishes its course and is gone. So the susceptible is going to be based on how many susceptible I had before. And then we said we were going to subtract away or move people away from susceptible and into infected by multiplying together susceptible and infected. So to get the multiplication, I'm going to click on the cells above, because then it will automatically update as I go. But I don't really want to multiply 108 by 2 and get 216 and say that's how many people are moving. I'll have negative people and that won't work. So I'm going to make sure I attach to this my probability, and I've got that written over here as K. And of course, when we're using that, make sure you put your dollar signs on your value so it won't move as you're going downward. And I'm going to just kind of drag a few of those down to see that it's going to be auto-populating. So this particular group that I moved out of susceptible, I'm going to copy that particular little chunk of code, and I'm going to say those people are actually moving into infected. So I grab the previous infected amount and I add in the group who left susceptible, now they've gone over to infected. So that's going to have people moving from susceptible to infected, and we can see that dynamically I get slightly different, I get growing numbers of infected people as we're going, which makes sense, they're moving from one category to another. I do also need to get some moving from infected to recovered. To do that, let me think about the recovered column first. It's a little easier to think about because there's only one way to get to recovered, and that's to come from infected. So we're going to get our previous recovered people who just stay put, they stay in recovered. And then I'm going to multiply my recovery rate, and again, watch your dollar signs on this one. And I'm going to multiply that by however many people were infected on the previous day. Now you might notice that we have decimals there, and we like to think of people as whole numbers most of the time, but when it comes to modeling things with statistics and with our differential equations, It's okay to have fractional people. They're not really fractional people, they're the chance that people are ending up in that category. So we're imagining on this day 1 after day 0, day 1 we have a quarter of a chance that somebody is sitting over there in recovery. By day 2, we have a 60% chance there's at least one person there. By day 3, we're thinking there's at least, probably at least one and a quarter, so one whole person and maybe 25% chance there's another person in there. At this point, I do have this nice little total I'm doing over here that adds up the 3 columns to make sure I haven't lost anyone or gained anyone. And if I pull that down, you're going to see I've been gaining people. That happens a lot in these models. Where did they come from? Well, I can tell you when I had people recover and they were added into the recover group, I didn't subtract them from the infected group. They left infected and went to recovered, so I'd better move them over. So I'm going to subtract the group who showed up in recovery. And when I do that, I just need to populate that downward, and I'm going to get my number of people stabilizing. So now I'm going to take my results here, and I'm going to populate it the rest of the way down. And I have mine set up to do 25 days worth of following our trends, and I can do that with my 110 people over here. And fortunately, they're staying at 110, so that's a good sign for my model. And now I'm going to get a quick little plot of what's going on here. So if I build a plot, something like this, I should probably title it. We'll call it our SIR model with k equals 0.006. So what we're going to see in this particular model is that we've got the blue line is susceptible. We start with a lot of susceptible people and they drop off because they get sick and they leave susceptible and go into infected and then recovered. Our infected people starts low because there's only a few sick. They get a few other people sick who get a few other people sick, and it goes upward, but it starts going down again later because people are moving from infected to recovered and because we're running out of new people to get sick. So we only have 110 total, we can't go any higher than that. And we can see that gray line is our recovered line. It started with no one recovered and then it went up from there. The yellow line at the top with the total doesn't tell us anything interesting, and I really don't need it in my plot. It was just there to reassure me that nobody got lost in my model, and there weren't any people that I was missing. So that's what my model's looking like right now. Before I go in and show you what the differential equations for this are going to look like, I did want to show you just a little bit of what happens if we play with our model. So I'm going to take this model that I built, and right now I've got a k value of 0.006. So that's my probability that an infection passes between people when they have an interaction. If I were to increase this, maybe instead of a regular environment, I'm on a cruise ship and people are hanging out with each other a lot more and they're in close quarters, I'm going to see my infection rate go up faster. If I made it even higher and it was at 0.006 and I doubled it to 0.012, we can see it spike faster. If I could lower it down to 0.003, which is half of what I started with, we can see it takes a lot longer to run through the infection, but it seems to max out with only having about 30 people sick at a time. So when they talk about flattening the curve, this is what we're talking about. So I'm going to put this back at 0.006 because that's what I put my label at. Finding out what exactly that K value is requires us looking at real world data that we'd have to pull in and match to this. And I'll show you what I mean by that in a moment or two. So let's go over here. This is our math modeling with differential equations class, so there should be a way that we can write down an equation for what we're seeing in the model we just played around with. So each of these 3 different equations talks about our rate of change. The first one is our rate of change for susceptible. If we think about susceptible, we only have people leaving that group, so our rate of change should be a negative value. And this is where I use my coefficient k. It's an unknown. I think it's about 0.006 for this particular problem. And then I'm going to multiply that by my I for the number of people who are infected. And then I'm going to multiply that by S in order to get the number of susceptible. Isn't it cute? It says KISS, which is probably a good way to transfer illnesses, so you shouldn't do that. And then for my infected, I'm actually going to have that same little piece of information, that same KIS, but this time they're getting added in because they're being moved out of susceptible and into infected. So I'm going to have, actually I'll just copy paste that from up here. Oh, I lost my K. So there's the KIS of people coming in. And then I also have people leaving infected, and I use the letter R for my my recovery probability. I said it was 12%, so you can put in a specific number for that. And I'm going to multiply that by I, because I is the number of people who are infected. So I have a sense of how many people could move from one to another. And then this R times I is going to be the number of people who are joining my recovered. You'll notice these equations look a little bit different than what I entered into Excel because they're only talking about the difference, not the updated values. To get the updated values, you take the original value or the prior line and you add in what your change is. So those are my differential equations. And those are my two models. Oh, this is one of my favorite tasks to do. What if we wanted to check if our model is accurate? How do we know if our model is accurate? Well, we need to go out and we get data. So I'm going to show you what it would look like if I had data and I wanted to make my model fit existing data, in particular playing around with our K value to get it to fit the data. So if you look at all of those little dots and curves going on there, you might be able to tell that the actual data is that light blue one, and that's the one that looks particularly not smooth, because real data often doesn't look very smooth. So I've got an Excel sheet that has that real data in it. Let me pull that up. And here's my sheet with the real data in it. It has the same model we had before, and the only addition to this one is that I have one more column, J, with some real data in it. Now, the thing I want to match when I talk about matching models, I want that orange line that tells me my prediction of how many people will be sick. I want it to match my blue line. So I can play with the recovery rate, or I can play with the K value. I'm going to play around with K value on this one. And it looks like, according to my real world blue data in there, I want to slow down the rate of infection. So I'm going to try dropping from 0.005 to from 0.006 to 0.005. And I see them a little bit closer. Let's try 0.003. Oh, now it looks like I'm not getting folks sick fast enough to match what happened in the real world. So we can try it with a 4. That looks like a pretty good fit. You can see how that orange line seems to cut through where the blue one is. It's not going to fit perfectly, but it does kind of show us what our overall trends are going to be. Now for one more question or one more thing to think about before we finish today with this little video, let me pop back into the PowerPoint. This is the what if part. What if there was a quarantine? What if some people were carriers but they didn't actually get sick? What if people could get sick twice? What if some people were immune? What if your model needs to be more complicated because the world you live in can handle more than just 3 categories of people? So what else could we do with our SIR model? Well, we could add more letters to it. Right now, we've got an S, an I, and an R. And let's just think about who else we might want to add. So if we did an SIR, those are kind of standard. We tend to keep those. But I could add a Q for quarantine. Then I can get people moving from susceptible to infected using something like some sort of coefficient K times I times S. But then sometimes my infected people will put themselves in quarantine. And when they put themselves in quarantine, they stop infecting other people, or at least they really reduce the odds they're going to infect other people. So if we say we put some people up here, maybe half of our infected people, they go to quarantine. Then they leave quarantine and they go to recovery, maybe at the same rate that they were recovering before, but at least they're not infecting other people. Some people are going from infected to recovered without going to quarantine, so I can get models that have more pieces to the puzzle. I could also have people who are susceptible going to infected or carriers. Carriers are infected, but they don't look sick, so they won't show up as being diagnosed sick. They'll just be infecting more people, and that's going to cause us to get more infections, and we'll get something like, let's add together the I and the C to get more susceptible people or more sick people. So I could have more pieces to my puzzle. I could also add a quarantine, and I could have them recover. So there's lots of ways to make these models more complex, and to play around with them and to fit them to data. And that's your introduction to SIR models.